Hey everybody. So this week we're going to be talking about various kinds of clustering techniques. And I want to set the tone by giving us a little bit of a background in the math that gets used repeatedly in clustering. Okay, so let's dive in. The first thing we need to talk about when we talk about clustering is the very idea of clustering is predicated on the idea of a metric. Clustering is this idea that we can take a bunch of data points, and some of these data points are more similar to each other than another part of the data, which is more similar to itself. And these two parts of the data belong to two different clusters. And one fundamental idea of that is that, things within a cluster are more similar to each other than they are similar to things outside the cluster. That idea of similarity is captured mathematically, formally, in the definition of a metric space. Okay? So a metric space is operating in a vector space, right? The idea here is that we have some sort of vector space. X is a vector space. Maybe X is, in the vector space of three-dimensional real vectors. It doesn't matter, we don't have to define that a priori, but we need to know that X is representing some vector. Okay, so what is a metric? Well, a metric takes some vector space, and in fact, it takes two measurements in the vector space, and it takes those two measurements and produces a single scalar value that lies somewhere between 0 and a finite value that's just less than infinity, whatever the heck that is, right? Somewhere between 0 and infinity. Fundamentally, you'll note this stuff is non-negative. There's no such thing as a negative distance, okay? It operates in real numbers. And anything which is a metric has to have the property of taking two vectors in a same vector space and mapping them to this single scalar value. Additionally, it has to have these qualities, right? If we're measuring if we put the same vector into both of these slots, well, we'd better get a distance of 0. If and only if we put the same vector into the two slots. Another thing is that a metric space should be symmetric. That is, the distance between x and y should be the same as the distance between y and x. And then the last one you'll recognize as the Pythagorean theorem, right? At least in Euclidean space, it's the Pythagorean theorem. The idea is that the distance between x and y has to be no bigger than the distance between x and z plus the distance between z and y, right? So to make this blindingly obvious to you, that's the picture you should have in your head. Okay, so we use these metric spaces all the time in machine learning. We have to talk about the distance in between different data points for all kinds of reasons, not just clustering. This works even in supervised learning. Now, we can define these metric spaces variously. If you're looking at the Euclidean space, well, the Euclidean space is the one where this is the distance, right? Between x and y. That distance is, xz squared plus zy squared, square root of that whole quantity. Right? It's just the Pythagorean theorem, that's the distance. In Manhattan or taxi distance or L1 space, well, it's just going to be xz plus zy, because in city block space, you can only go around the city block to get to the destination. You can't go charging all the way through it like you can in a Euclidean space. Okay, other things that you might come up with. We mentioned the L norms, right? The idea that an L norm is just the elements of the vector to the pth power, add up all those elements, and then to the minus, to the, this square root is negative power, right? Am I crazy? I'm totally locked up on whether it's to the negative power or to the 1 over n. It's to the 1 over n, to 1 over p. God, Jason. All right. If I just force myself to write it, I can actually see it. So the p of something is, of some vector x, is going to be the square root. No, it's not a square. It's to the whatever, the pth root of x1 to the pth power plus x2 to the pth power plus. All right, that was a digression as my brain locked up from a lack of caffeine. Okay, but in general, other things that we might do, they are stuff like z-score distance. Last time in lecture, we looked at the way in which we can do multivariate Gaussians, right? And we had Mahalanobis distance. Mahalanobis distance is the interior of the exponential in a multivariate Gaussian, right? It's the vector x minus the vector mu transposed times the covariance matrix times the vector x minus the vector mu. Another thing that we haven't talked about is the Hamming distance, which assumes that every single element of the vector is a bit. It's 0 or 1. So the Hamming distance is a special case that we use for binary features. All right. Lots of metric spaces. They're all fun and useful. You should get to be comfortable with the ideas, at least, and hopefully eventually the math behind all of these. Okay, so given that we've got a set of points and we want to cluster them, it might be useful to know where in space is closest to one of these points. All right, so if I place a new data point here, which of these prototype vectors is the closest to my new data point? So the idea of figuring out where inside a vector space is closest to a prototype is done using something called Voronoi regions. Voronoi, of course, is somebody's name, somebody Slavic. I'm possibly not pronouncing it right, but this is what I generally hear people say as Voronoi. Okay, so given this set of p points, how can we find all the parts of a region that are closer to this data point, I'll just mark it in red, than any other? Okay, well, the way you can do this is that we can take, for all the nearest neighbors to this point of interest, we can draw the line to those nearest neighbors. Okay, so let's assume those 4 data points are correctly all the nearest neighbors. Now, what we can do is, well, what region here is going to be closer to this point? Well, take any one of these lines, go halfway along it, and everything from halfway and closer is definitely closer to this point. So, all right, that means that the halfway point, right? And that generalizes. You can just draw a straight line that is perpendicular to this line between the data points. So let's assume that I'm freehanding this somewhere close to correct, right? And everything on this side of the line is going to be closer to our point of interest. Okay, we just got to keep doing that. So that's for this one. Okay, and for this other data point here, maybe the bisecting lines like that. And for this data point here, maybe the bisecting lines like that. So these bisecting perpendicular lines define the region where anything that falls in this region is closer to this point than it is to any of the others we've defined. So closer, what is closer? Well, it matters. What metric space are we using? The way I'm drawing this and the way you're thinking about it is in Euclidean space. But FYI, this could be Manhattan space. And things would look different in Manhattan space, L1. All right, so let's animate this and see what's going on. So if we start at any one of these data points and we grow outward until we meet the other growth circle, you're going to see something, if my freehand was any good, wasn't the worst. You're going to see something close to what I drew. So this Euclidean growth, a spheroid growth, where those two things meet, forms lines. Those lines can be defined as the perpendicular bisectors of the lines in between the 2 points, right? And that forms this so-called Voronoi diagram. Each one of these regions is a closed region. Each one of these regions is formed of straight lines. Each one of those straight lines is a perpendicular bisector of the line in between a pair of points. Okay, so this Voronoi tessellation or Voronoi diagram shows us which points are closest to a particular prototype vector. So let's talk about k-means clustering, right? Now we have some language to describe what's going on. We've picked a metric space, probably Euclidean distance. And within a vector space, in this case, I'm showing you a two-dimensional vector space, right? We're operating in a vector space that's in two-dimensional reals. And we're using a Euclidean norm. We're measuring distance the way the crow flies. Okay? And we're assuming there are k sets of clusters. And in particular, we're assuming these clusters are convex. What does convex mean? Right? Remember, this is a convex curve. This is not. Okay? So a convex cluster, like you're seeing here, a Voronoi region is a convex cluster. We also critically, some of the assumptions in here is that each cluster is defined by its mean vector, by its centroid, by those little white x's. Okay? And what it means is this assumption of equal variance, well, that just lets us use the Voronoi region itself as saying all data points within the Voronoi region belong to that cluster, right? So every data point is assumed to be generated by the closest mean, by that white X that's inside the Voronoi region. So all these purple data points are all assumed to be noisy measurements of some process that has a mean here. Okay, that's not too hard. It's a pretty simple concept, but we've got some math backing on it now. So what's the algorithm that generates these clusters? we need to choose the centers of those clusters. Those centers are going to be denoted as mu, right? So this is a vector, mu. And what we're trying to do is we're trying to minimize that Euclidean distance squared. So take the Euclidean distance between a given data point and the cluster it's assigned to, and square that distance. So we sum that up over every single data point that's assigned to that cluster, and we sum that sum over all the possible clusters. And our job is to pick the clustering, right, the sets of mu's that minimize this total double sum. Now, note that we have this definition here. What's the mean of a cluster? Well, the mean of a cluster is really just take all the data points inside the cluster and add them up, and then divide by the number of data points in the cluster. Literally, this is just the empirical mean of all the data points. So this immediately starts to suggest to you how we're going to solve this, right? First thing we need to do is, given a clustering, calculate the mean of each cluster. And then, given where means are, well, we're going to assign data points to clusters. And we're going to go back and forth, back and forth, back and forth between these two steps. Okay, so here is an implementation. Note that the implementation is different than the math we're trying to optimize, right? We got to add some details for the computation. So the first thing we do is we need to start with a set of centers, centroids, means, right? And, there's a lot of ways to do this, but one way, the dumb way, the simple way, is just take those data points themselves and pick k of them at random and call them the means, okay? So now we've got a bunch of data points. And we've got a couple of means. Well, we need to make that Voronoi tessellation. We need to say, hey, all the data points which are over here belong to the green mean. And all the data points that are on this side belong to the purple mean. So we're going to assign each data point to its closest cluster. Now we recalculate the exact means based on these empirical assignment of data points. Maybe at this point, the mean shifts. It's no longer these ones. Maybe we now have something like this. Okay? Again and again and again. Iterating this until the total distance on each loop that we're doing this, the total distance the means have moved, is less than some threshold, a convergence criteria that once this threshold is reached, the means are shifting only a tiny, tiny amount, we stop updating. Okay, now, interestingly, this turns out to be also a completely different idea that can be described by the same math. Vector quantization is the idea that we want to compress vectors, right? Instead of keeping all this, however many dimensionality this is, like what if this thing is like R100? That's a lot of data. Well, instead, wouldn't it be nicer if we just said, oh, there's 10 means? And instead of having a 100 long vector, we can just keep a number between 1 and 10 and replace the big vector with lots of data with just a number between 1 and 10. So that's the idea, that we compress an image, right? Like JPEG is a compressed image format. What we do is we throw away the exact data that was in the original image and we replace it with quantized versions of the data. We chop up what was a continuous number into a discrete set, and we replace the real valued number with just which element, which quantized level we're going to be representing here. This works remarkably well, and it is exactly the same math as k-means. In fact, you can also use this not just for quantizing an image to compress it, but you can use this for categorization, where we say, hey, whatever cluster you belong to is the category you belong to. So this implementation of this, the last time we talked about k-means was an online algorithm in the sense that we were iterating until convergence, but we were operating on all the data in batch. We were operating on all the data at once. So you can do vector quantization in a doubly online sense. We keep iterating until convergence, just like in the k-means case. But what we also do is we operate on each data point individually. So we pick a data point at random. We find the closest prototype vector to it. And we move the prototype vector some amount less than 1 towards the data point. Okay? Usually a lot less than 1. Usually that eta term here is actually much less than 1. Okay, and we keep doing that until some convergence criteria is reached. So this is online in the sense that we only operate on one data point at a time. So that's it. That's vector quantization, which is the same thing, it turns out, as k-means, which we went through all the fun stuff like Voronoi tessellations and metric spaces to get you to understand all this. All right, thanks very much. I'll talk to you in class. Bye.